Today's discussion session is about these two topics: the limit of a function from section 2.2 and find the instantaneous velocity of a moving object from section 2.1. I picked 3 problems to present today. The first problem is the problem number 21 on page 69 in the book. Sketch a graph of function f. Function f is defined here. And use the graph to make a conjecture about the values of function value f4. Left-hand side limit f4. Right-hand side limit f4, and both side limit f4. Now, let me sketch the graph of this function first. Because this function is defined piece by piece, so I sketch its graph also piece by piece. Let me draw a XY plane. XY plane. 0 here. The first piece, when x is less than 4, then the function is square root of x. Suppose 4 is here. Square root of x. For a square root, x cannot be negative number. Say square root of -4. If you use a calculator, then calculator will tell you error, not computable. So when x is less than 0, low function value, therefore low graph. So the graph of square root of x is between 0 and 4. When x is a 0, square root of 0 is 0. When x is 4, square root of 4 is 2. So the graph look like this. Because x is less than 4. So at 4, x is 4. Low square root of x. So I put an open dot here. Open dot means the point is not part of the graph. At 0, function value is 0. So solid dot here. Solid dot is part of the graph. First piece. Now second piece. When x is equal to 4, function value is 3. Function value is the height of the graph. This open dot, the height is 2. So 3 is about here, number 3. So solid point, solid point, solid. This is part of the graph of function f. Now the third piece. When x is greater than 4, the function is x plus 1. X plus 1, the graph is a line. To draw a line, I need only 2 points on the line. When x is 4, x plus 1, the value is 5. 5 here. This is a 5. 5 here. 5. Pick a second point. Say when x is 5. 5. When x is 5, x plus 1 is 6, about here. Now join these 2 points with a 9. Again, because x is greater than 4, not equal to 4. So at 4, this point should be an open dot. This point is not part of the graph. This is the graph of this piecewise defined function. Now, use the graph to make a conjecture about these four values. The first one, function value at 4. Solid point is here. Height of graph is function value. So this solid point, the height is 3. So function value at 4 is 3. Now, second, left-hand side limit at 4. X approaches 4 from the left side. What number the function will approach? To answer this question, let me take X on the left side of 4. Say pick X. The height of the graph at X, this height is function value at X. As X approaches 4, this height will approach the height of this open dot. The height of this open dot is 2. Therefore, this limit is 2. Now, about this limit, right-hand side, right-hand sided limit at 4. X approaches 4 from the right side. 4 plus means from the right side, greater than 4. X is greater than 4. Now this time, let me pick an X on the right side of 4. Right side, say, yeah, X, pick X on the right side. F of X, function value at X is the height of the graph at X. Yeah, this height is F of X. This is a F of X. As X is closer and closer to 4 from the right, this height is closer and closer to the height of this open dot. The height of this open dot is 5. Therefore, right-hand sided limit at 4 is 5. Now, last, both sided limit. Both sided limit, independent variable X can approach 4 from the left or from the right. By the convention, we call that there are 2 conventions about a limit. Second convention says that the limit should be 1 and only 1, unique. When I let X approach 4 from the left side, I got a limit 2. When I let X approach 4 from the right side, I got a different limit. So therefore, is both sided limit. We say that doesn't exist. When X approaches 4, function value approaches more than 1 number. So in this case, we say that the function has low limit at 4, doesn't exist. This is example 1. Now, example 2. I also pick a problem from the book to present. Let me see. Problem number 46, page 70. 46, page 7. 46, page 70. Sketch the graph of a function. With the following conditions. Function value at 1 is 0. Function value at 2 is 4. Function value at 3 is 6. Left-hand sided limit at 2 is -3. Right-hand sided limit at 2 is 5. Yeah, we need to sketch a curve that satisfies all these conditions. Now let me draw an XY plane. XY plane. 0 here. 1, suppose 1 is here. 1 is here. 2 is here. Number 3 here. Now, first condition. Function value at 1 is 0. Function value is the height of the graph. Function value at 1, the height of the graph at 1. The height is 0. So, solid dot here. Solid dot is part of the graph, is the graph. Function value at 2 is 4. Function value at 2 is 4. Suppose this height is 4. Solid dot 4 here. Function value at 3 is 6. 6, suppose, is here. So 6 here is here. Right. Now, this condition. When x approaches 2 from the left-hand side, function, the height of the graph approaches -3. 2. X approaches 2 from the left side. The graph, function value, height of the graph approaches -3. Say -3, suppose here. So the graph, like this. Because this point is not part of the graph, so I put an open dot here. Part of the graph is this solid point. And also this point on the graph, it is not function value. Function value at 1, function value as f at 1 is 0. So solid point should be here, not here. Let me erase. Not here. Yeah, let me erase. This point on the graph is not function value. Function value at 1 is 0. Function value is here. So let me put an open dot here. Open dot. That means that that point is not the function value at 1. The final condition, x approaches 2 from the right side. Function approaches 5. The graph of of the function approaches 5. 5 is about here. X approaches 2 from the right side. The graph approaches, the height approaches 5. So the graph approaches 5. Here. Open dot. Yeah. Open dot means the height of this point is not the function value. Function value is here, solid dot. And also free. X is free. Function value is 6. The height of this solid point is function value, not the height of this point is the function value at free. So I put an open dot here. Open dot. Yeah. This is the graph of the function that satisfy these conditions. There are many possible solutions. This is only one solution. Say the other solution, you can draw the curve like this. You see, yeah, a second solution. Yeah, you can draw the graph like this, right? There are many possible solutions. This is just one of the solutions. The third example today, I take a problem about the second topic, find instantaneous velocity of a moving object. Example number 3. This is the example number 1, section 2.1 in the book, page 56. This example says that a rock is launched vertically upward from the ground. With a speed of 96 feet per second. Initial speed is 96. A well-known formula. A well-known formula from physics states that the position of the rock after t seconds is given by this function. S here, S means position of the rock. Negative 16 t squared plus 96 t. The position is measured according to this unit. The position is measured in feet. The time, t is time, is measured in seconds. Okay, now this is the ground. Right? Some person throw a rock upward a rock upward. Yeah, upward. Upward. Yeah. In this example, the upward direction is a positive direction, and the downward direction is the negative direction. Negative direction. Now, several questions. Question A: find the average velocities of the rock on the following time intervals. Yeah. 1 to 3. Second time interval is a 1 to 2. 1 to 2. Now let me answer this question first. Now solution. The average formula, average velocity formula is okay. Average velocity of a moving object on a time interval t1 to t2. The formula is location, position at t2 at the right end point of the time interval minus position at t1. Then this is position at t2 minus position at t1 is the distance traveled by the object over the time interval, or the distance traveled, yes, or the displacement of the object on the time interval. Yeah. Then over time elapsed from t1 to t2. How much time elapsed? t2 minus t1. So much time elapsed. This is the formula to compute average velocity over a time interval. Now, let me apply this formula to answer part A. Average velocity on the time interval from 1 to 3 by formula position at 3 minus position at 1, then over 3 minus 1. Position at 3. This is position at a general time t. Now I plug in number 3 in t. Negative 16 times 3 squared plus 96 times 3. It is 144. Now minus position at 1. Plug in 1 in t. Negative 16 times 1 squared plus 96 times 1. The position is 80 feet from the origin. Then over 3 minus 1. So it is 32. Average velocity, the unit feet per second. Similarly, average velocity on the time interval 1 to 2 by formula position at 2 minus position at 1 over time elapsed. It is position at 2, 1 28 minus position at 1, then over 2 minus 1. So the answer is 48 units feet per second. This is question A. This example has several questions. Question A. Now, question B. What is the velocity? V means velocity. Velocity at 1 of the rock at time is 1. This question is asking instantaneous velocity at 1. How to find instantaneous velocity at 1? We cannot use average velocity formula. Why? Because average velocity on the time interval. It is a single time moment. The time interval is 1 to 1. How to compute average velocity on this time interval? Time interval contains a single point. If we still use average velocity formula, see what will happen. Position at 1 minus position at 1, it is 0. 1 minus 1 time elapsed, 0. What is this? 0 divided by 0. I don't know. So this time, average velocity formula doesn't work in finding instantaneous velocity. Now, then how to find instantaneous velocity? We use limit. We use average velocity to approximate instantaneous velocity. From pi A, we have compute average velocity over the time interval 1 to 3 is 32. Now, I can guess, okay? Velocity, instantaneous velocity at 1, roughly is 32, not exactly. Also from pi A, average velocity over the time interval 1 to 2 is 48. Now I have a new guess. This new guess is better than 32, this guess. Why? Because 1 to 2, this time interval is shorter than the time interval 1 to 3. Yeah, this 1 to 2, this interval is closer to this interval than this interval to this interval. So 48 is a better guess, okay? Instantaneous velocity at 1 now, I guess, is 48. But 1 to 2, this interval is still too large compared to 1, 1, this interval. Now, let me make a table. In the table, I decrease the length of the time interval. Yeah, let me make a table. The first column is interval. second column is average velocity. Over the time interval 1 to 3, we got average velocity is 32. Over the time interval 1 to 2, average velocity is 48. Now, I decrease the time interval, the length. Over the interval 1 to 1.1, average velocity is 62.4. Over the time interval 1 to 1.01, average velocity is 63.84. Then time interval from 1 to 1.001, average velocity is this number, 63.984. And over 0, 1, this interval, average velocity is 9,984. Now, from this table, when the time interval is decreased to 1, this interval, then average velocity, I can see that is approaching 64. Then 64 is exactly instantaneous velocity at 1. So the answer to part B is velocity at 1 is 64 feet per second. This is instantaneous velocity. This is question B. Now, question C. What question C is? Oh, C. Sketch the graph of the position function. You can use your graphing calculator to do this part, but I don't have graphing calculator. But I know that the graph of a polynomial, this is a polynomial in T. The graph of a polynomial of degree 2, quadratic polynomial, is a parabola. Because the leading coefficient, negative 16, is negative. So the graph, this parabola, is open downward. Let me draw the graph. Horizontal line is time. Vertical line is position. When t is 0, plug in 0 in t, then we get the value of s is 0. So this point is part of the graph. And when x is 6, I plug in 6 in t, then the position is 0. Yeah, this point is part of the graph. Now, parabola open downward, so the graph looks like this. Parabola open downward. Parabola open downward. This is question C. Question C. Now, Question D. So that an average velocity is the slope is the slope of a secant line. Solution. Let me pick one average velocity from part A. Say, pick average velocity over the time interval 1 to 2. Average velocity on the time interval 1 to 2 is equal to location at 2 minus location at 1. 2 minus 1. This is 48. 48. Now 48 is the slope of a secant line. Which secant line? Suppose 1 is here. 2 is here. Corresponding to 1 on the graph is this point. Corresponding to 2 on the graph is this point. Now join these 2 points with a line. This is a secant line, not a tangent line. Now the slope of this secant line. Slope. How to compute the slope of a line? We have the slope formula. Slope formula says that y2 minus y1 over x2 minus x1. So 2 points. Yeah, this point, x coordinate is 1, y coordinate function value at 1, because this point is on the graph of this function. So y coordinate is function value at 1. And this point is on the graph of this function. So x coordinate is 2. Function value is 2. Function value is 2. Now 2 points. y2 minus y1. Which point is y2? Doesn't matter. Let me choose s of 2 as y2. So s of 2 minus s of 1 is y1. Then over x2 minus x1. X coordinate of this point is 2 minus x coordinate of this point 1. Okay, you see, this is the slope of the green line, but this slope exactly average velocity. See, so this is average velocity on the time interval 1 to 2. Yeah, so an average velocity is the slope of a secant line. This is D. Now, question E. Question E. So that the instantaneous velocity v of 1, instantaneous velocity at 1 is the slope of a tangent line. Which tangent line? Actually, the tangent line at T is 1. That means that the tangent line at this point. Let me draw tangent line. Tangent line. Tangent line. The slope of this tangent line is v of 1, instantaneous velocity at 1. Why slope of this blue line is instantaneous velocity? Solution. Slope of okay, let me explain in this way. From puppy here, from puppy, we saw that instantaneous velocity at 1 is equal to the limit of average velocity, right? Yeah, this is instantaneous velocity. You see, it is the limit of average velocity. But average velocity is slope of secant line. Right? This is part D, right? Average velocity is slope of secant line. Right? But the green line, as the time interval 1 to 2 decrease, the green line is approaching to the tangent line, the blue line. So the limit of slope of secant line is equal to slope of tangent line. Tangent line at 1, right? The green line, when the time interval 1 to 2 is decreased, right? When the time interval is decreased, the green line is approaching the blue line. Therefore, slope of the green line approaches slope of the blue line. In other words, limit of slope of the secant line is equal to slope of tangent line at 1. Therefore, instantaneous velocity at 1 is slope of a tangent line. The tangent line at 1. Okay. Today I present these 3 problems. See you next time.